So hello everyone, welcome to lecture number 7 actually for modern semiconductor devices for integrated circuits. This is lecture number 7. Alright, so we have covered the following semiconductor physics fundamental topics, that is evolution and uniqueness of semiconductor technology, then equilibrium carrier concentration concept, thermal equilibrium concept of quasi-equilibrium. Yesterday we have seen wave particle duality, then intrinsic and extrinsic semiconductor we have solved numericals also. Then we have also seen the energy band diagram of intrinsic and extrinsic semiconductor. We'll also see this topics today, that is carrier transport. Carrier transport are of three types: drift, diffusion and thermoelectric current. Then we'll also see about what is random motion of charge carriers, drift and diffusion process. What is the concept of excess carriers? This I've explained in brief, but we'll go in details today. Then the injection level and carrier lifetime. And finally, we'll conclude this small module by direct comparison between direct and indirect semiconductors. All right. So yesterday I've given you all, before leaving this numerical, for N-type silicon, donor concentration is 10 raised to 17. Okay. So what is donor concentration given by Na or Nd? Nd. That is 10 raised to 17 per centimeter cube. Now, what are they asked to find out? Find out minority and majority charge carriers. So, how will you find majority and minority charge carriers? Let's do that. So, what will be majority charge carriers? Assuming complete ionization, that means here it's a N-type silicon, right? So, what are the majority carriers? NNO, right? NNO is equal to ND, which is 10 raised to 17 per centimeter cube. Are you understanding? 10 raised to 17, right? Huh. 10 raised to 17 per centimeter cube. What will be minority carrier concentration? PNO will be Ni square divided by Nd or NNO. So what is Ni square? 1.5 into 10 raised to 10 square divided by NNO will be Nd, which is 17. So what is the number which you are getting? 2.25 into 10 raised to 3, which is quite small. This carrier concentration are quite small. So understood how to write it down if you have not completed. Right, majority carrier concentration is this and minority carrier concentration is very less. So this is majority carrier concentration and this will be minority carrier concentration. And then we have to plot the energy band diagram. Well, this is the energy band diagram. Okay, so this is the energy band diagram for N type silicon. All right, now how will you find EC minus EF? There was a relation, right? EC minus EF will be KT natural log of NC upon ND. Yeah. So let's write that down. EC minus, actually what was the formula? EF. The Fermi level was given by EC minus KT natural log of NC upon ND. NO is ND, na? It is NO or NNO is equal to ND over here. Okay, so what will be EC minus EF? It will be KT natural log of NC upon ND. And how much is NC? From the constants, na? Let me cross check it. 2.8 into 10 raised to 19 per centimeter cube. So let's find out EC minus EF, which will be KT. KT is how much? KT is 26 millivolt, that is 0.026 milli electron volt. Okay, so that will be 0.026 milli electron volt multiplied by natural log of how much is ND? NC 2.8 into 10 raised to 19 divided by 10 raised to 17. Can anyone tell me how much is this number? 0.146 electron volt. Milli electron volt nahi. Okay. You have considered the year milli? Huh? Just check it, cross check it right now. Check this number. You have to use calculators. You should have your calculators with you. This is all hard work which we have to do. Acha, before doing anything, how much is this total distance? 1.1 electron volt. How much is this distance? Electron volt. And now we are finding EC minus EF, this one. So that has to be in electron volt only. So check this answer. Please check this answer with your calculator. Don't just write it down. So these type of numericals are expected in exams. Zero 0.026 calculator you all have. 146 electron volt. What is natural log of 2.8 into 10 raised to 19 divided by 10 raised to 17? What is that number? Go get the calculator. Natural log of 2.8 into 10 raised to 19 divided by 10 raised to 17. Sorry? Electron volt, no? So this number is 0.146 electron volt. Okay. Now we have to find EC minus EI. What is that number? I mean, what is the formula of, do we have a formula relating EC and EI, EF and EI? What is it? Yeah. So what we can do is, what was the formula? EF is equal to EI, right? Plus KT natural log of ND upon NI. Actually NNO, right? NO, right? So it will be as follows. What do we want? EF minus EI. EF minus EI will be KT natural log of NNO. This will be what? ND, right? ND upon NI. What is NI? 1.5 into 10 raised to 10 per centimeter cube. This is intrinsic carrier concentration. So how much will be this? This will be 26 milli electron volt. Oh, this will be 0.026 electron volt. Huh? This is electron volt. Now it is correct. Okay, so into natural log of ND is 10 raised to 17 and divided by Ni is 1.5 into 10 raised to 10. So how much is this now? EF minus EI is 0.408 electron volt. So this number is 0.408 electron volt. Alright. So this way we can do the analysis similarly for p-type semiconductor also. So there everything will be with respect to the valence band. Got it? I think earlier numerical we have done it for p-type semiconductor. But it was a compensated semiconductor. Compensated semiconductor, that was p-type. So we have done p-type and one n-type. Okay. Completed everyone? What? Numerical? This energy band diagram. This is the energy band diagram for n-type silicon. Acha, I'll draw it for p-type silicon just for a reference. So write down, draw energy band diagram for a p silicon. Okay, p-type semiconductor or silicon. So how will you start? First of all, you will draw valence band and conduction band. Okay, then at the center what will come? Intrinsic carrier concentration will be at the middle of energy band gap. All right, now since it's a p-type semiconductor, p-type silicon, you will have donor level or acceptor level, and acceptor level is closer to valence band, very much nearby. Minus or plus? Yeah, this is EA. Okay, acceptor level. Then where will you have Fermi level? Fermi level is different, slightly closer to valence band or conduction band? Valence band. So this I am drawing it little separately. So this is EF. You can write EF or EFP. Yeah, correct. Now here, this is the diagram, okay? And here you can mark what is the energy band gap for silicon. So Eg will be 1.1 electron volt. Now, what another type of numerical can be asked is this. So this EI level is how much? EI level is around 0.55, exactly at the center, no? Let's say this level is 0.35 electron volt, and this EI is EA, you know how much is this distance, right? This distance you already know. Now given this information, you need to find majority and minority charge carriers. So if there will be a question that find, this is a p-type silicon, right? PPO and NPO for this diagram. So let's find out that. Do you know have any formulas for that? Yes, PPO is given by NV exponential of minus of EF minus EV, right? Divided by KT. Yes or no? This is the formula. Actually, this 0.35 is this distance. Okay. So in the given data, this is 0.35 electron volt. So do we have EF minus EF minus EV? Yes. So what will be PPO? NV. What is the constant NV? How much it is? 10 raised to 19, right? Or 10 raised to 18 it is. 10 raised to 19, right? Huh. So it is 10 raised to 19 exponential of minus of EF minus EV. How much it is? 0.35 electron volt. How much is KT? 0.026 electron volt. So electron volt will get cancelled. Yeah. Now find out this number. How much is this? PPO. This is exponential of e raised to minus of. How much is that? Please let me know. 7 point exponential of minus 6. 1.42 into 10 raised to minus 10 raised to 10. 13. Are you getting this? Can you Acha, that multiply by this, multiply karna hai. So did you get this? Same number? Okay, these are the majority carriers. What will be minority carriers? NPO, Ni square upon PPO. So this will be 1.5 into 10 raised to 10 square divided by 1.42 into 10 raised to 13. Calculate this. 1.05 into 10 raised to minus 3. Huh? This is 10 raised to 20. This is 10 raised to 7. So around how much you will get? 1.5 into 10 raised to 10, the whole square divided by 1.42 into 10 raised to 13. Something. 10 raised to, it cannot be negative. 1.05 or 1.5? 1.05 into. So one thing, if you notice over here, if the majority carrier concentration is quite small, the minority carrier concentration is also quite high. When the majority carrier concentration is very high in the range of 10 is to 17 or 18, minority carrier concentration is quite less. Are you understanding? So these are your majority and minority carrier concentration for p-type silicon. And this is how we draw the energy band diagram. Understood this? Is it 1.05 only? Okay. Okay, fine. You have the calculator, so you know the answers. Okay, can we go ahead with the next one? Acha, 1.5 into 10 is to 7. 1 point into 10 is to 7. Okay. All right. Okay. Next concept which we are discussing today is injection level concept. Just write down the heading. Okay. For your ISC exams, let me show it to you. Right now we have considered module number 1, which we are already doing, which we are going to complete this week. So in module number 2, you have small section of it, 2.1 only, PN junction diet, and module number 4, which ma'am will start in from next Monday onwards. Ma'am will take the lectures on module number 4 directly. So we have part of module number 1, 2, and 4. This is for your ISC exams. One we are already completing, and we have solved numericals also. So and 1, 2, and 4 part of it, not completely. We have 2.2, 2.3 also. So it's a part of it. Okay. So here we'll have module number 1, 2, and 4. All right. This we are already completing, right? This we are already on the verge of completing. 1.1 and 1.2. That is module number 1. Yes, yes, exactly. That is not much. That is PN junction only. This This will complete in 5 to 7 lectures. So maybe by next month we will be completing module number 2, which will be much ahead. And ma'am will start with module number 4. And we have a small section of it only for your exams. Alright, so you'll be easily able to complete the ISA syllabus on time. Don't worry about it. Okay, so write down injection level concept. So write down what it refers to. It refers to the extent to which it refers to the extent to which semiconductor is disturbed. It refers to the extent to which semiconductor is disturbed from equilibrium. From equilibrium. Because of excess carriers. Because of excess carriers. Okay. What did I say? Small deviation from. I mean, the semiconductor is disturbed from its equilibrium. That is called as quasi-equilibrium. I told you, na, small deviation from. So here, let's consider the charge balance equation. So let's write down the charge balance equation. And let's say we have both N-type and P-type impurities. That is a compensated semiconductor. So what is the formula given by? Do you remember? P naught plus Nd plus is equal to N naught minus plus na N A minus. This was the it, right? Yes or no? This was the formula, right? Now let's say how do we modify it? So how I'm modifying it as follows. I'm writing not at equilibrium. This O stands for equilibrium. I'm writing P plus Nd plus minus N minus Na minus. I can take this on left hand side, right? Easily. And this I am multiplying with delta. Delta means small deviation from. So here I can say delta P minus delta N is equal to delta Na minus minus Nd plus. Alright. Now we have one assumption that if the change in the ionization of impurities is negligible, if change in the ionization of impurities is negligible, then this number will be 0. Na minus, the number of ionized carriers for acceptor and donor will be almost same because change will be negligible. Then this number will be 0. If this number is 0, we can say delta P is equal to delta N, right? So here you can write, assume change in ionization of impurities is negligible. So delta P minus delta N will be approximately equal to 0. So we can say delta P is approximately equal to delta N. So this delta stands for, excess carriers, and this is the situation in most semiconductors. So this is the meaning of excess carriers being generated in pairs. So what does that mean? For every extra excess carrier hole, there will be an excess electron. And this is the situation in most semiconductors. So this delta, what does this delta mean? This delta P is equal to delta N is equal to delta. What does the symbol represent? Symbol represents excess carriers over and above the equilibrium value. All right. It's a very important concept, excess carriers. And here it means that the excess carriers have been generated in pairs. For every hole, there will be an excess electron. So it's a pair. So that is, if I want to write in terms of equilibrium concentration, how we can write P as, can anyone tell me? P will be P naught plus delta. Okay, and N will be N naught plus delta, excess carriers. Where what is P naught and N naught? Equilibrium concentration of electrons and holes. Write down. Equilibrium concentration of electrons and holes. Okay, completed this much. Now we'll divide the excess carriers into three levels. Completed. Okay, the x-axis now will be in the log scale. So draw it along with me. This is representing excess carriers. This is a log scale. Log scale meaning you can fit large magnitudes. So let's say we have divided this into three sections. This is majority carrier concentration divided by 10. This will be 10 into majority carrier concentration. So let's say we have n-type semiconductor. So this level will be high level injection. This is high level injection. Short form HLI. This will be, if majority carrier concentration is divided by 10, then it is called as low level injection. All right. And in between them, we have intermediate level injection. Intermediate injection level. This is LLI. Intermediate injection level. Okay, let's take an example. So let's consider n-type silicon. N-type silicon, what are the majority carriers? N and O. Okay, that is around 10 raised to 18. So what is low level injection over here? Majority carrier divided by 10. So how much that will be? Correct? And what will be HLI, the high level injection? 10 raised to 18 multiplied by 10. That is 10 raised to 19. Got it? So low level injection meaning if your concentration is, let's say, for example, hypothetically 10 lakh, it is divided by 10, it will become 10,000. Understanding? And if my high level injection means what? If my high level injection, normal carrier concentration is 10 lakh, I mean 1 lakh, it will become 10 lakh. So from 1 lakh it is stopping down to 10,000 and 1 lakh is becoming 10 lakh. So that's the difference between high level and low level injection. Remember, whenever you have excess carriers, the minority carrier concentration will be distributed. What do you mean by that? Let's see an example. So write down for delta less than majority carrier concentration divided by 10, that is low level injection, N is equal to NO plus less than NO by 10, correct? Plus delta we write na. Earlier we have written N is equal to NO plus delta. And what is delta over here? NO divided by 10. So this is approximately equal to NO. That means by increasing the injection level, majority carrier concentration is not getting disturbed much by low level injection. How it is not getting disturbed much? Earlier, let's say NO is 10 raised to 18. Now it has become what? N is equal to what? 10 raised to, oh, not so much actually. NO is very that not that much great. Let's say 10 raised to 14. 10 raised to 14 plus 10 raised to 13 it will become, right? This is around approximately equal to 10 raised to 14 only. Got it what I'm saying? 10 lakh plus 1 lakh will be approximately 10, I mean, that way. Are you understood? So majority carrier concentration will remain same almost. Let's say about the second one for high level injection, that is delta greater than majority carrier concentration into 10. What will happen to N? N is NO plus greater than 10 times NO. So which is approximately equal to delta itself. Excess carrier concentration itself, na? So N will be equal to delta, which is excess carriers. This is high level injection. Now let's take an example. The last topic will be taking an example. Let's take an example to understand high level and low level injection. Can I go now to the next one? If you have a query or a doubt, you can ask immediately. Yeah? Okay. Let's go over here. Now let's take an example. So example of low level injection and high level injection. So question is, we have N-type semiconductor. So where Nd is given as donor concentration is given as 10 raised to 5. It's a phosphorus doped silicon. What do you mean by phosphorus doped silicon? N-type. So let's say low level injection is delta 1, which is 10 raised to 12 per centimeter cube, and high level injection is delta 2, which is 10 raised to 17 per centimeter cube. Now we have to plot all of them in concentration scale. Concentration scale will be, I am plotting it vertically. This is concentration in log scale, because you cannot plot 1 lakh and 10 lakh and 10,000 on one scale. That is why we have a log scale. Okay. Now, first of all, I will plot my intrinsic carrier concentration, where it is somewhere around here, which is Ni, approximately equal to 10 raised to 10 per centimeter cube, which is Ni. You know what is Ni, right? What is Ni? Intrinsic carrier concentration. Okay. Now tell me, where will be your majority carrier concentration N naught? I told you now over here, see, for high level injection, N will be approximately equal to delta. So where it will be? For low level for high level injection, where it will be? 10 raised to, so somewhere around here, right? N2, we can say N2 means high level injection, and that will be how much? Approximately equal to P2 also. Why P2? High level injection may doesn't matter. Either we have a, huh? Delta is equal to delta P delta N, right? We have written na. So what will be this? N2 will be equal to, or let's write N2 will be equal to delta 2, which is how much? So this will be 10 power 17 per centimeter cube. How much will be N1? Actually, I think this is 10 power 15. This is not 5, this is 15. Just make that correction. These are majority carrier concentration, no? 10 power 15 it is. This is 10 raised to 17. So this is actually high level injection, right? High level injection. Okay. How much will be N1? 10 raised power 15. Array, for LLI, what happens here? See, you have written na here. N will be equal to N naught. And N naught is how much? ND, which is for low level injection, it is here written low level injection N is equal to N naught. So how much is that? Around 10 raised to 15. So what is this? N1 approximately equal to N naught, approximately equal to ND. So this is under equilibrium. All right. Acha, what is minority carrier concentration P naught? See, N naught P naught is given by Ni square, and Ni square is approximately 10 raised to 20. So what will be P naught given by Ni square upon N naught? Consider this to be 10 raised to 20. Okay, divided by N naught. N naught is how much? 10 raised to. So this will be 10 raised to 5. Minority carrier concentration, no? So where you can plot this minority carrier concentration? Somewhere around here. So this is 10 raised to 5 per centimeter cube, and this is what? P naught, minority carrier concentration. Understood? For low level injection, where is P1? For low level injection, where will be P1? No. P1 for low level injection. This is high level injection, na? For low level injection, where will be P1? Wait. What will come over here? 10 raised to 12. What will settle down? What will come over here? This is delta 1, right? This is low level injection. What is this delta 1 equal to? Excess carriers for low level injection, right? So what will be this? N1, N1 is to equal to N0, right? What will be this? Equal to P1, P1. P0 to is here, na? Minority charge carriers is here. This is Ni. 10 raised to 12 also somewhere should come, na? So what it will be? See, from here you get any clue? For low level injection, how much it will be? Acha, what is N1? N1 means what? Corresponding to low level injection, na? And under equilibrium, that is equal to ND only. N1. What will be P1? So you're saying P1 will be approximately equal to? See, N1 is under low level injection, right? This, what is happening over here? This is minority carriers, na? Hana? Now here minority carriers is 10 raised to 5. Now we apply, listen. Now we apply low level injection. Now we apply low level injection. और low level injection का concentration कितना है? 10 raised to 12. So what will be P1? 10 raised to 5 or 10 raised to 12? 10 raised to 12. You're injecting excess carriers. So minority charge carrier under equilibrium is how much? 10 raised to 5. When you're injecting it with 10 raised to 12, it becomes 10 raised to 12. So this is actually equal to P1. Got it? So minority carrier concentration is disturbed here. I've given you the attendance sheet, na? Sign on the today's date only. Recording chalu hai, recording. So what do you learn from the above discussion? We learned that for low level injection, the minority charge carrier concentration is disturbed a lot. From 10 raised to 5, it has become 10 raised to 12. Whereas majority carrier concentration is almost same as equilibrium. For high level injection, both minority and majority carrier concentration are almost the same. Okay. So write down this inference. Does you have understood this diagram? Yeah. So write down the inferences. That is the learning from here. First, for low level injection, minority charge carriers or minority carrier concentration is disturbed. While majority charge carriers or majority carrier concentration is almost same as equilibrium. This is under high level injection or low level injection. Then for high level injection, both majority and minority carrier concentration are almost same. Okay. So here we end the lecture. Next time we'll see how these excess carriers will affect the energy band diagram. Got it? The concept of low level and high level injection? Yeah. P1. Huh. Huh. Approximately same. P1 is approximately equal to that only. What I'm saying is, see, equilibrium is 10 is to 5. It is drastically becoming 10 is to 11 or 10 is to 12. So that's what the point is. Low level injection के लिए minority carrier concentration is getting disturbed from 10 is to 5 to 10 is to 12, whereas for high level injection both are remaining undisturbed, same as your equilibrium concentration. Okay, that is the learning we take from here. These two inferences what we have written. Okay, so next lecture will start with the effect of excess carriers on the energy band diagram.